All right, the last kind of volume we're going to find is volume of solids with known cross sections, which we've been doing, okay? Because when we did the disk that we started off with, that little rectangle was a cross section of the region they gave us. Once we revolved it, the disk was a cross section of the solid. And what we did is we found the volume of one little cross section, then we found the volume of 1,000,000 of them, then 1,000,000,000 of them, then 1,000,000,000,000 of them, and we added them all up. We're going to have the same idea here, okay? So follow with me. Since area equals pi r squared is the area of a circle, the integral used with the disk method, volume equals integral from a to b of pi times radius squared dx, can be generalized as volume equals the integral from a to b of the area of the cross section dx, where a of x represents the area of a cross section, dx is still the thickness of it. Okay? So it's still a volume, not just adding up areas of things. Okay? So, well, in other words, what we've been doing is actually a special type of finding a solid with known cross section. But in my mind, it makes more sense to go in the order we did, which the book does, and every book I've ever used does, because sometimes we do things this way. For instance, in geometry, you know, it turns out at the end of the year, I told you something about how congruent figures are actually a special type of similar figures where the scale factor is 1 to 1. But it would have been a tougher thing for you to learn what congruent figures were if we had started with similar figures. So even though congruent figures are actually a type of similar figures where the scale factor is 1 to 1, we started with congruent figures. So even though having disks or washers is actually a special type of a known cross section, it's convenient to start there because they're all the same. Okay? It's like, okay, the first assignment, they're all disks. So all I have to do is find that radius and I'm good. On the washers, they're all washers. So if I find the outer radius and I find the inner radius, I'm good. They're all the same after that. With known cross sections, though, instead of always having a disk or a washer, now your cross sections may be squares or triangles or other odd creatures. Okay? Which in theory doesn't make any difference. But what does make it different is, well, now they're all different. Okay? And so it's harder to get in a groove. You can't just say, okay, I've figured out it works this way. I'll practice it 10 times. I'll be good at it. Because now all the cross sections are different things. And what I'm saying so far makes sense to you? Okay. So let me come back to this screen in just a minute. So if we have something like this is on page 461 in your book, and I don't have neat little animated things to go with this. I have some, but all they do is show you different views of it, which isn't very helpful, I don't think. But here's the thing. If you look at these two, both of those figures are made by the same region, but the cross sections being perpendicular to different axes, not an axis of revolution anymore, okay, just the x-axis or the y-axis, them being perpendicular to a different thing, you get a slightly different shape. Can you tell that those two figures are not the exact same? It's kind of hard to tell they're not the exact same. If you look inside of them, okay, on the one on the left, these cross sections are perpendicular to the x-axis. Now look, they've turned this. Here's the x-axis, okay? And on the other ones, the cross sections are perpendicular to the y-axis, that being the y-axis. And so the little squares you've got inside of there are slightly different than each other. Okay? But it's going to be the same idea. If we're doing squares, then we're going to have little bitty prisms, right? And if it's a square that you give a height to, its volume would be length times width times height, right? So then that's how we'll add those up, okay? But the different cross sections give you different figures. And I wish they'd give, what I wish they'd done with the little animated thing is I would have liked to have seen the graph on the XY plane and then them show you putting in more and more little squares until it was a solid. And then if it was a triangle that was the cross section, show them putting in a bunch of little triangles until it forms that solid. I don't know why they didn't do that, because I think that would be very helpful. And I'm not a computer programmer. I can't do it myself. Okay? But you get the idea? If we look here, here's a region, and then the cross sections are equilateral triangles. So you see that little bitty equilateral triangle in there? Right? There. Okay? So we might have to find volumes of, well, you can't say volume of a triangle, but when the volume of anything, now I can go back here, I guess. The volume of many things is the area of the base times the height. That works for a prism, right? Not prism. So if our cross sections are equilateral triangles, find the area of that, multiply it times the height, not of the triangle, but the dx or the dy. That would be the height, making it a solid instead of just a triangle. And that'll give you the volume of that triangular cross section. Okay? Maybe the cross section is a regular pentagon. That's capital B. Find the area of that regular pentagon, that's capital B, times the dx or the dy. That makes it a solid instead of just a flat pentagon. That's the volume of it. All right, so that's the general idea. When we have the A of x dx, A of x is the area of the cross section, dx is the height of that itty bitty little solid. Okay? That's what makes it a solid, not a two-dimensional figure. Does that make sense? Now, remember how we always said that the rectangle, when we were doing disk and washer, had to be perpendicular to the axis of revolution? And that's how we figured out the dx or the dy. All right, here's what you need in your notes. If the cross-section is perpendicular to the x-axis, we're working with x's. And the volume of that solid will be the integral from a to b of the area as a function of x dx. And if the cross-section is perpendicular to the y-axis, the volume will be the integral from c to d of the area of that cross-section as a function of y dy. Remember, dx or dy, that's what makes it a solid. That's what gives it a height. All right. Let's work this example I have here on the slide. You don't have to write all this down. Write the work down, and I'll give you a copy of the problem later if you want me to. So, here's our example. A pyramid, 3 meters high, has a square base that is 3 meters on a side. Square base. Can we find the area of a square? Hopefully. The cross-section of the pyramid, perpendicular to the altitude, x units down from the vertex. is a square x units on a side on the volume of the pyramid. All right, so first we try to draw it. So I've got the x-axis, I've got the y-axis. I can put the pyramid, well, I need to put the pyramid the way I've got it there. All you see is the side view, but all right, a pyramid, 3 meters high. Now, you see 3 on there a couple of times. Which one is the 3 meters high? That one. Here's why. That is 3 meters on a side. The cross section perpendicular to the altitude, x units down. So I've got to make a cross section perpendicular to the altitude, and I've got to be able to say that it's x units down. So I need the cross section to be here, x units down. I did that first, then I built the pyramid around it. That needs to be my cross section because of the way they described it as x units down. So, not necessarily this time I did. Okay, this time I did. So, I've got that. I'll call it x. It's x units from, oh good, from the origin. That makes sense. X units down. Okay. All right, from the vertex. All right, so that needs to be the pointy part of the pyramid right there. That's the official word, the pointy part. That's the book definition. Okay, so then I did that, and again, that's obviously not the whole pyramid. I'm looking at it side view. It's laying on its side, isn't it? The altitude is the x-axis. Well, the x-axis goes through the altitude of this pyramid. Okay? Now, it says the base of the pyramid is 3 meters on a side, so that's where that 3 comes from. And then the pyramid is 3 meters high. That's where that 3 comes from. Everybody with me? So you just kind of piece it together. There's no always do it in this order kind of thing here. I figured out what they were talking about. Okay? Now, find the volume of this pyramid. Well, the way I've drawn this, the cross section is perpendicular to the x-axis, isn't it? So use what I have highlighted in yellow. So use this. Since the cross section is perpendicular to the x-axis, the area will be a function of x. And then I know how to find the area of a square. They tell me that the cross, since it's got a square base, doesn't every cross section have to be a square? Okay? If it was a triangular base, every cross section would be a triangle. If it was a pentagon for the base, every cross section would be a pentagon. Yes, they'll tell you. It's a square base, so every cross section is a square. And I know how to find the area of a square. It's side squared. So, x squared. You with me? Now, turn it into an integral. So, volume equals. All right, now, I didn't do this, and I should have. Let's go ahead and turn this into, give it a height there, that cross section. What's the thickness of that cross section? It's dx, okay? So the area of the cross section is a of x. The height of it is dx. Now, since I'm dealing with x's, the limits of integration have to be x coordinates. So I'll put the vertex of the pyramid at the origin, and then the base of the pyramid is down here at x equals 3. So the integral from 0 to 3. Make sense? All right. So that's the integral from 0 to 3 of x squared dx. What's the integral of x squared? 1/3 x to the third from 0 to 3. So that's 1/3 times 3 cubed, that's 27, minus 1/3 times 0 cubed, that's 0. So that's 1/3 times 27, 27 thirds. 9. Okay? Now, for this particular problem, we could have done geometry instead of calculus. For a pyramid, volume equals 1/3 times the area of the base times the height. 1/3. What would the area of the base be? Not a cross section, the base. 3 squared. 9 times the height. What's the height of that pyramid? 3. And we get the same thing. Okay? All right. Let's see. Let me try something here. Let me go ahead and show you the animation for these graphs. Maybe it'll help you, even though I didn't think it helped me any. All right, so that's graph. Those are the graphs of the same thing. Here's all they do. I mean, it helps you see that it's a three-dimensional figure, but I don't know, is that helpful in any way? I didn't think it was. All right, let's look at that next graph. It does kind of help you see the cross section in there a little bit. Those cross sections are rectangles. Let's see what's the next one. These cross sections are triangles. At least you see different views of it, but that's about it. I really wish that they would have been able to start with this, because here's, if you graph all this that you see over here, that gives you that shape. That gives you, let's see, I need to move back over here. And it annoys me too a little bit that they move the x and y axis around, because your whole life, x-axis, y-axis, right? So look, that's the x-axis, that's the y-axis. If you graph those three, you get that. And so what I wish the animation showed us was little equilateral triangles growing up out of that space. Because see, if you start here at the tip, that'd be a teeny tiny little equilateral triangle, because the sides along the graph would be so teeny tiny, right? Then you get here, and so now that base is bigger. It's, for it to be equilateral, those sides have to grow as well, correct? To keep it equilateral. So when you get here and that segment's larger, then those sides have to be larger to keep it equilateral. That's why it has to be, your area of the cross section has to be a function of a variable. It can't be a constant, because as the segments that you can make connect going from one side of the drawing to the other get bigger and bigger, well, then the sides of that equilateral triangle have to get bigger and bigger. You know, if we back up to here, if we have cross sections perpendicular to the x-axis, all right, see where the x-axis is. All right, so if I first had one, let's see, I'm not even sure I can draw this to make it look like anything. All right, they've got one that's fairly small. So if I started here and went out here, I've got to have, well, I can't do it. I can't draw it. That's why I wish they had the animation. But do you see how all the cross sections are going to be different sizes due to conforming to the original graph that's on your XY plane? Okay? So it let me down with the animation a little bit there, but oh well, we'll get over it. All right, let's do an example. All right, let's do part of number 61. All right, number 61. It says find the volume of the solid whose base is bounded by the graphs of y equals x plus 1, all right, that's a line, and y equals x squared minus 1, that's a parabola, with the indicated cross sections taken perpendicular to the x-axis. All right, so perpendicular to the x-axis, what variable are we going to be working with? X. Okay? So, I did not look at their graph from the book first. Well, I did, but I didn't mean to. Okay? I didn't mean to. All right, I want to draw the graph myself first. So I did. There's the graph of y equals x plus 1, and there's the graph of y equals x squared minus 1. And then the cross sections have to, they go between those two graphs. They're bounded by those two graphs. So I drew in a representative rectangle, okay? So I started with just like this. All right, then I realized, okay, it's got to have some thickness, otherwise it's just a two-dimensional figure. I've got to be adding up volumes. Back to integration as an accumulation function. I'm not accumulating areas, I'm accumulating volumes. So my cross-section has to have a little bit of height to it, okay? So thicken it up a little bit. Oh, that turns it into a rectangle like we've done a million times before, okay? Now, for part A, the cross-sections are squares. So that means that that little blue segment, if I take that little blue segment off of that graph, I can just redraw it right there. That little blue segment, so that little blue segment becomes that one. It's a side of a square, isn't it? Isn't it? Since they tell me the cross sections are squares. So the little segment that I make being bounded by those two graphs is one side of a square. So there's the square. Now, if I made another cross section right there, it'd be a smaller square, right? And if I made another cross section right there, it'd be a smaller square, right? So all the squares have different sizes. All right, so now I'm going to work to look at what the book had. Okay? So you can barely see it here on mine, but there's a square in there. So that, and I cannot visualize what it's going to look like myself. I can't. Just by seeing what I've graphed here and knowing that I get squares, I got no clue what it looks like as an actual solid. Do you? I mean, I don't. So I'm glad they did give us that. So, there's the little square inside of there. And it does grow into a solid. Okay? So in other words, it's in the graphs they give you as the basis for making your little cross sections. Okay? So drawing your rectangle, and that'll be, or at least if you draw in a segment, that'll be one side of whatever they tell you the cross sections are. Does that make sense? All right. The further apart the two graphs are, the bigger the cross section. And the more it sticks up off of your coordinate plane, right? Because it's hard to tell here, but right there would be itty bitty little square. It doesn't stick up off your paper much. If you visualize this as growing off of your desk, which is about the only way I have a chance of visualizing it. So you've graphed that. It's sitting there on your desk, and then little bitty squares are growing up out of this region. The further apart the two graphs are, the bigger a square it takes to connect the two graphs. The closer the two graphs are, the smaller the square it takes to connect the two graphs. Does that help you visualize it just a little bit? Maybe, maybe not. All right. So, doesn't it all come down to this? Can I figure out what the area of that square is? That's what it comes down to, right? Because if I can figure out what the area of that square is, and I don't mean as a number, I mean as a function with x's in it. If I can figure out what the area of that square is, I can integrate the integral from a to b of that area, remember a of x, dx. I can do that. I promise I can. You can too. The hard part's figuring out what's the area of that square look like. Okay? Everybody with me? Let's figure out what the area of that square looks like. And it's going to take me a few stages. Once you've done enough of these, this goes a little faster, but I want to make sure you're with me. So, here's the way I'm starting. The first thing I want to do is figure out what the base of that cross section is. So, the length of that little red segment right there. Okay? That length would be the y-coordinate on top minus the y-coordinate on the bottom, wouldn't it? That's the length of that little red segment. So the y-coordinate on the top is called x plus 1 because that's the graph of y equals x plus 1. The y-coordinate on the bottom is called x squared minus 1 because the graph on the bottom is the graph of y equals x squared minus 1. So when I combine all of that, that's what the base of the cross section is. Okay? All right. Can I now find the area of that square? If I know what one side of it is, I can. So, and I know this is confusing, I did this next. So I did that first. I'm doing this next. Okay? How do I find the area of that cross section? If one of the sides of a square is negative x squared plus x plus 2, every side of the square is negative x squared plus x plus 2. So the area is going to be that squared. So then so I figured that out. You with me on reasoning that through? So then here was the third thing I did. The area of the cross section, that's my a of x, equals base times base, side times side, side squared, base squared, negative x squared plus x plus 2 squared. All right. Is that written in a good way to integrate it? Not particularly. So, look, I might be done with this step in a different problem because by doing that, it might be written in such a way that's easy to integrate. This is not easy to integrate. So what do I need to do? I need to actually square that out, don't I? And there's what happens when you do. All right, so I'm ready to integrate. You ready to integrate? So the volume accumulates the volumes of these cross sections. Okay? So volume equals integral from A to B of the area of a cross section times the height of the cross section. A of x is the area of the cross section. Dx is the height of the cross section. All right. I'm not ready to integrate like I thought I was. Because what's A? What's B? So, here's the fourth thing I had to do before I can actually solve this problem. I got to find the intersections, right? I want to know the x-coordinate where they intersect there. I want to know the x-coordinate where they intersect there. How do you find the intersection of two graphs? Set them equal. So, set the first graph, x plus 1, equal to the second one, x squared minus 1, and solve it. And now I know that A is negative 1 and B is 2. And now I'm ready for the fifth part. And this is the easy part. All right, did you follow me all the way through this? Here's the fun part. If those weren't squares, would it all work out just like this? Finding the base of the cross section could be the same, right? But then finding how to get the area of the cross section, well, that'll be different, which means step 3 will be different. Step 4 ought to be the same, okay? But when you get different cross sections, you know, it's good. You got to take that into account. All right. You get the antiderivative, you plug, you chug, you get 81 over 10. Hey, at least that's only 2 problems. Yeah, they like that part A, part B stuff, don't they?